use the substitution method to find all solutions of the systems of equations. When we look at this system, we see that the coefficient of y in the first equation is 1, and the coefficient of x in the second equation is 1. And so those two variables are good candidates for being isolated in the first step of the substitution method. I'm going to isolate the y in the first equation to get y equals minus 2x plus 7. I'm now going to substitute that into the second equation, that is y written in terms of x, into the second equation to get x plus 2 times negative 2x plus 7 equals 2. And I will go ahead and simplify the left-hand side. Collect the like x terms on the left and subtract 14 from both sides. Dividing by negative 3 gives the value of x to be 4. Now, I'm going to back substitute that value of 4 into the first equation where we wrote y in terms of x. And so now I'm going to get that y equals negative 2 times 4 plus 7, or negative 1. And so the solution is the ordered pair 4, negative 1. This is the point where the two graphs of the two lines cross, and it is the only pair of values that will make both equations true. Notice 2 times 4 is 8, plus negative 1 is 7, and 4 plus 2 times negative 1 is 4 minus 2, or 2. So both equations are satisfied, so we say the system is satisfied. Now, it's not very common to have the coefficient of one of the variables equal to 1, so substitution does not get used all that much. In the second system here, we see we could use fairly simply substitution again because of the coefficient of 1 in the second equation, but instead we're going to use the elimination method. And in the elimination method, we want to multiply both equations by an appropriate value so that the coefficients of one of the variables are opposites of each other. And thus, when we add the resulting equations, one of the variables will be eliminated. And so in this case, I'm going to multiply the second equation by negative 3. Now, this is not the only way to proceed, but this is what I'm going to do. I'm going to take negative 3 times the second equation. I'm going to put a circle around 2 to mean the second equation. So the first equation is unchanged. The second equation becomes negative 18x minus 3y equals minus 99. So when we add, we get negative 15x. The y's neutralize each other, equals negative 75. Dividing by negative 15 gives us x equals 5. And now we can substitute x equal to 5 into either of the equations. I'm going to substitute x equals 5 into the first equation. That will give me 3 times 5, which is 15, plus 3y equals 24, which in turn gives 3y equals 9, or y equals 3. So our solution is the ordered pair 5, 3. Again, we check. 3 times 5 plus 3 times 3 is 15 plus 9, which is 24. And 6 times 5 plus 3 is 30 plus 3, or 33. This is the only ordered pair that satisfies both of the equations. It is their point of intersection. And in the third example here, I'm going to multiply the top equation by negative 2 times equation 1. That's going to give me negative 8x plus 6y equals negative 62. I'm not going to do anything with the second equation because I already have the coefficients of the x opposite of each other. And when I add, I will eliminate the x's and get 10y equals negative 50, or y equals negative 5. That gets substituted. I'm going to substitute it in the first equation that I've written down here. And so negative 8x plus 6 times negative 5 is negative 30 equals negative 62. Negative 8x equals negative 32, or x equals 4. So our solution is the ordered pair 4, negative 5. 4 times 4 is 16, minus a negative 15 gives us positive 31. 8 times 4 is 32, minus 20 is 12. And so the solution does satisfy both equations and therefore is a solution for the system.